All right, so thanks very much. And yeah, so Anushya is the second speaker for the session. And she's going to talk about theory of the numerically accessible many-body localization transition. Thanks, Anushya.
Okay, great. Thank you very much, Tom. Thanks very much to all the organizers for this invitation. Sorry about the Zoom troubles. I don't know. Clearly, I'm too old to figure out Zoom. But this is I know this is primarily virtual conference and random circuits, but a number of you who are attending have broader interest in quantum dynamics, and in particular have worked on many-body localization and its aspects before. So a lot of you who are listening in have worked on many-body localization before. So I thought this would be interesting to present to you. We're hoping to post this by the end of the week, but it builds on some previous work that Philip Crowley, who was my postdoc and is now moved on to MIT, and I have done together. And I should say, Phil is the one who's really led the charge on all this stuff, and I, in the last 2 years, learned a lot about MBL from him. A special thank you to Dries and Anatoly. They're our colleagues at BU, and you'll see that we're going to disagree with them, but we've had many conversations which have been productive, and we have agreed to disagree. So it doesn't happen often, and so thank you to them. And I hope I'm presenting their work in the right light. Okay, so I'll keep it short and sweet. What is many-body localization? Let's just think in a concrete setup that was the setup that motivated Anderson's original work in 1958, which is of the question of spin diffusion in an inhomogeneous medium. So we have some kinds of localized entities, we'll call them sites. We're going to think about one-dimensional geometries today, so we arrange them on a line. Each of these localized entities is going to has an internal degree of freedom, a spin. We will think about models that have some kinds of interactions on this graph that respect the 1D geometry. For example, JS.S. And then an inhomogeneous medium is modeled by a random field. And that's what I have up there. And the strength of that field is going to be W. So you'll start seeing W over J around, and that's what this W and the J are. So the question that motivated Anderson and has had a long history since then is basically what is the dynamics of this system under its one Hamiltonian. In particular, as you vary the strength of the inhomogeneity as compared to J, do the spin transport dynamics or energy transport, does it all remain diffusive? And we're going to ask this question today at infinite temperature. We could ask it at any energy density. We're going to do infinite temperature, which is kind of the, which means we're thinking about states with very, very high energy density about the ground state. Energy density corresponding to infinite temperature. Okay, so a lot of you know what the current consensus is in terms of this question, this dynamical phase diagram at infinite temperature. So very weak inhomogeneity, W over J. You'd call the dynamical phase thermal. What are its characteristics? Well, within quotes, it's classical in the sense that if you focused on a local subsystem A, which I have up there as 2 spins, whatever is outside it, the complement A bar, looks like a bath. You can model it as a bath at some temperature, and thus describe the relaxational dynamics of A. And in particular, it means A reaches thermal equilibrium at the same temperature as the surrounding bath as T to infinity. There are some wrinkles about whether the transport will remain diffusive or one dimension is quite special. Subdiffusion is possible, but I'm going to sweep all that under the rug and just call all of that thermal. Okay? Of course, this talk wouldn't exist if there was no belief that as you crank up W over J, goes strong in homogeneity, there's something different that happens. This is dubbed many-body localization. Now, this is quantum within quotes. Now, what does that really mean? The way I understand it is to say that instead of what surrounds A bar is functioning as a big, infinite bath, instead, despite having these infinite numbers of degrees of freedom, it appears like a few-level system. So A's dynamics can be described as if it's coupled to another few-level system. So in particular, the quantization of the energy levels are visible in the dynamics. You see like oscillatory things, hence the word quantum. A second feature, or related, is the fact that if you imagine following the dynamics starting from some state, a local subsystem retains memory of its initial conditions, even as you evolve for longer times. Okay, and then of course, what happens in between, transition, is what's going on the side? These have been questions that have occupied people for many years. But there's been consensus that somehow these are the right phases on either side. And yes, we need to figure out what goes on in between them, and that will give us insights into quantum dynamics more broadly. But MBL is a thermodynamic, non-ergodic phase, dynamical phase. That's the belief. So this is a set of recent works, starting from Thomas Persin, Lev Vidmar in 2020, and more recently from our colleagues down the corridor, Dries and Anatoly Polkovnikov, where they just claim that MBL is absent of the thermodynamic limit, right? So this is going back to the first diagram, first phase diagram I had. They're just saying, I think it's diffusive all the way. And let me just quickly place their arguments in some context, because that was our motivation. Okay, so what do they actually do? And I should say, these papers have studied various different numerical, various observables numerically. I'm going to focus on the spectral function because that's what we're going to calculate. So they're going to calculate the disorder average spectral function. It's defined here. It's the Fourier transform of this correlator, the ZZ correlator on some site n. Okay, and in these papers they approached this. They approached numerically, try to compute and understand this spectral function coming from the thermal side of the phase diagram that I showed you. All right, so I'll quickly summarize what my understanding of their main messages. What they give numerical evidence for is that when you plot this spectral function on a log-log plot, there is an intermediate set of frequency scales in which you see this kind of 1/omega behavior. And if you Fourier transform that, what is that telling you? That's kind of telling you that the ZZ correlator on a site is decaying very, very slowly, like just, logarithmically in time. Okay, that's very slow. And then they have arguments that say this kind of behavior cannot persist to arbitrarily low frequencies. In particular, basic some rules that the spectral function should obey would be violated. I'm maybe putting words in their mouth. I don't think it's very important to them exactly what happens at lower frequencies, but the simplest answer is that it becomes diffusive. So they say there's this window of this 1/omega behavior at much lower frequencies. The square root 1/d omega encodes diffusive dynamics. And you'll see the scale that I marked in between omega sub L. And that kind of decides the time scale in which you'll see diffusion. The important point to take away from what I have below there is that it's exponentially large in W over J, but it's still finite. Okay, so they're in the business of saying there's no MBL thermodynamic limit. It's all diffusion just after very, very long times with very small diffusion constants. Now, a number of you are listening in have probably studied this problem before, numerically certainly, and you've seen some, depending on the measure you use, irrespective of the measure you use, I should say, you've probably plotted a diagram like this. It's thermal on one side, there's a critical value of W over J, there's some crossover physics to do with the fact that you can only do this stuff with finite size, and there's localized on the other side. So you say, but what of the fact that we see these things at finite size? And so then these authors would tell you it's a finite size effect. In particular, they compare this frequency scale. I have a typo there. It should be omega sub L to the Heisenberg frequency. But what they're doing is they kind of say the finite size level spacing cuts off this very low frequency diffusive behavior. That's what you're seeing as a finite size transition. And in particular, that predicts that this critical value of W over J, which you see behavior going from thermal to MBL, should scale linearly with L. And all of these authors provide numerical evidence for such drift with L at the sizes that one can do in diagonalization through various measures. Okay, so this inspired us to ask the question, can we take a simple model in which MBL is a stable phase and explain these finite size observations, in particular this drift and the features of the spectral function that I noted in the previous slide. So that's where we come in. That's what I want to tell you about today. So what we've done is a phenomenological study of this disorder of spectral function. and a simple model for MBL. So I'm not gonna tell you very detail what the model is right now. I'll tell you what our results are because I think that's more interesting, and then hopefully I'll have a little bit of time to tell you how we got there. But in case I don't get there, so what are we doing? Our setup is that there is some chain that is putatively MBL, and we connect a probe spin to it, and the probe spin, we're measuring the spectral function of this probe spin, and what goes into our calculation, what tells you that this chain is MBL, is the fact that the matrix elements of the operator that connects the probe spin to the chain has a structure by range. So the R subscript there is range, and it's kind of that the norm of this operator falls off with range, okay? Exponentially, and zeta, you'll see zeta now appearing in slides, subsequent slides, and that's what this zeta is. It's characterizing how a matrix elements fall off with range in the diagonal basis of a MBL chain. And then what are we doing? We're not doing anything fancy. We're just doing very careful resonance counting. And then statistically trying to work out what the disorder averaged spectral functions. Okay, so that's what we're doing. What do we find? We're actually able to explain, I hope to convince you of this, SNP, Selson-Polkovnikov's finite-size observations. More interestingly, we're able to make a set of predictions about the vicinity of the transition from the localized to thermal phase, both in the Floquet and Hamiltonian systems. So I kind of want to walk you through all these results, and and of course, please interrupt me and welcome comments. We're partially presenting this before we post it so that we can hear from you. Okay, so let me orient you and just tell you what the model predicts first in the thermodynamic limit. Okay, so the y-axis there is inverse system size 1 over L. Thermodynamic limit is 1 over L is 0. With that, the model, again, what the model means is just this model for matrix elements, how they're decaying in the diagonal basis. So it says that when that decay length is small enough, you have MBL. Then there's a critical value of the decay length above which it's thermal. So everything is inverted here because I plotted 1 over zeta. Okay. So this is what the model predicts in terms of when MBL could be stable. But you can now start, my title promises finite size effects. So let's start to say what happens as L goes to infinity, right? So, and what you see is something that should remind you of quantum critical cones. So we see that a critical delocalized cone, the yellow region up there, comes out from this point as you go to finite size, and it separates a thermal regime from an MBL regime. The C bar ZZ over there, I will explain just in a minute what that is and how that acts as an order parameter for us to be able to differentiate these two phases. Something else to take away from this plot, there is a length scale C that emerges, which is in the vicinity of the transition, diverges as this power to the -1, and that's what sets the shape of this cone to be linear, okay, when you make the system size finite. Okay, so this is kind of the bottom, and now I want to show you what the spectral functions do on either side of this transition I have as a yellow dot. Okay, so bear with me, there's going to be many powered exponents and so on, and two types of transitions, but I'll try to walk through it briskly, but hopefully clearly. So let's first focus on the transition of Floquet system. And I'm not giving you any details here, but all you need to know is this is a interacting strongly inhomogeneous chain that's being driven periodically by some torque. And in high enough frequency, this is believed to have stable MBL. So for our purposes, though, yeah.
A quick question. So when you had nu1 in the previous slide, that was just because that you're thinking about finite sizes and that's what's being observed?
No, so if you're going to talk about Harris, Luck, and such, I will comment on it in the end. So you see that I just didn't, it was too busy, this diagram with everything in it. But you see that I've kind of marked out this semicircular region at the very bottom. And so it is depending on whether you're talking about hyperuniform versus disordered or so on. So basically, depending on what the Harris-Luck behavior is, there can the truly asymptotic behavior, very long lengths, could be something else.
Okay, thanks.
Right. I assume that was your question. Why is this violating Harris-Luck?
Yeah. I mean, just yeah, that's right. Yeah.
Okay. Yeah. So so upfront, this could be the description of the truly asymptotic transition in sufficiently hyperuniform systems. In disordered systems, we think this is kind of a pre-asymptotic regime with like really Harris-Luck physics modifying what's going on in this bottomless block, and hence that semicircle. But thank you, and yeah, I was clearly pushing things under the rug there. Okay, so what's going on in the Floquet transition, by which we just mean there's no conservation laws and no energy, no spin, nothing conserved on this chain that's being driven periodically in time. Let's start with what you can see there. So we're looking at the vicinity of the transition. And as you're familiar with in terms of with continuous phase transitions, there's a frequency scale, omega sub c, above which what you see is the behavior of about which the spectral functions behaves as it would at the phase transition. Okay, so that's what omega sub c is there. It's going at the transition, it would be 0. But a little bit away from the transition, it's finite, and above that scale, you see something characterizing transition, which is a power law. I have to tell you what all these thetas are, and I will in a minute, but let me just orient you with what the behavior is in broad terms. There's one power law about omega c, and a second power law below omega c, which is different between the MBL and the thermal phases, which makes sense, right? Because low frequency behavior should be different, because low frequency is long times, and long times, you have to be able to tell which, if there are two different phases, you have to be able to tell which side you're on. So we don't have much to say about the thermal one. It is probably diffusive. Sorry, not diffusive. It's something to do with ballistic dynamics as Floquet system, but I'm not written a form there. But we can predict what it is in the MBL side, and there's a different exponent theta naught that characterizes that. So, what are all these different exponents? And in particular, how do they behave as you vary your distance from the transition? So on the left-hand side, I'm plotting what these exponents are. Again, the right, I should have written it, but it's written out there. You can see that the MBL is to the right of this 1 over zeta c, thermals to the left. So this exponent theta naught is defined on the MBL side, and it's going to 0, approaches 0, as you go towards the transition. Okay, so that is to say that this power law is going from omega to the 0 to 1 over omega as you approach the transition. However, at the transition itself, we predict that there is a discontinuous jump in this exponent, and instead it has a value that I have up there, where I wrote it up there just to tell you that at least within what we can calculate, it doesn't seem to be universal. It's set by microscopic scales. Omega there is the drive frequency, J is kind of the set scale of the interactions, and it's finite, right? So for the Floquet transition, we predict not 1 over omega spectral functions at low frequency of the transition, but omega to the -1 plus this theta c. Okay, and again, how do these behaviors square? The knee that you see in the blue curve on the right, omega sub c, just kind of goes off to 0 as you go towards this transition. So all you see is the exponent and behavior to do with theta c at the transition. Okay, so that was simply talking about the spectral function at finite frequencies. However, there is a delta function component. This is the part that's telling you if there is local memory on the prospin when you connect it to this chain. And that's what's the C bar CZ. So we expect it to be non-zero on the MBL side, 0 on the thermal side. And the graph on the right, just look at the orange curve, tells you what we predict, how this C bar by ZZ approaches 0 at the transition. So the transition, at the transition itself, there is no infinite time memory. So in that sense, it's delocalized. On the MBL side there, it approaches it as a, what is this thing called? Essential singularity. Okay, so, all right. So let me just go through that again for Hamiltonian transitions, which have energy conservation. I think it's interesting because it actually modifies what's going on at the transition. So same curves as last time. If you look below the scale omega c, that's the really low frequency behavior. You see something on MBL, something different on thermal. The state are not explained again appearing on the MBL side. Look above the scale omega c, and you see what will be the behavior at the transition. And now, instead of just it being a pure power law, it's a power law 1 over omega, which has this logarithmic front factors multiplying it, right? And that is completely a consequence of energy conservation, right? And if you plotted the exponent theta naught again, much like it did in the flow K case in the MBL side, it starts from, the power, the blue line goes from omega to 0 to something that's 1 over omega. But at the transition, there's no jump. Instead of the transition, there is this kind of basically 1 over omega, but corrected by these logarithms. Once again, you can ask what the, I'm really out of time. You can once again ask what the late time value is, the delta function in this plot. We have a form predicted for it. It's significant. It grows as you approach the transition from the thermal side. It takes off much faster than the flow K case, which is the orange curve there. Okay, so I promised that I would explain something about finite-size numerics. So let me get there quickly. So our result with energy conservation is on the left. My sketch of what cells in Polkovnikov say is on the right. You should compare red curve to red curve. And the bottom line is that we say that the 1 over omega behavior that they observed is likely 1 over omega with log to the 3/2 omega. The predictable power of the log there, I can discuss with you. There are different regimes for it, but definitely that it's corrected by a logarithm. We can also understand the scale omega sub L and how it relates to omega sub C. But that's it. This is how we're kind of explaining the spectral function. We're saying our red curve is their red curve, and really there are these logarithmic corrections that come out naturally from a theory that has a stable MBL phase. And in particular, that means that there are arguments for why there must be a low frequency cutoff break. So that's one. But more interesting, or maybe more interesting, is to explain what this finite size drift could be with resource strength over J, right? So this is just a summary of what I've been focusing on this regime. I tried to tell you there's a continuous transition, thermal, MBL, and then this critical code showing up at large finite sizes. But nobody believes that we're able to access very large sizes at using exact diagonalization. So if you go to smaller sizes, so higher up on this plot, we actually see a new length scale that emerges in this critical cone. And what it basically is the distance to the first resonance. So you remember what we're doing is we're adding a probe spin to the center of the chain, and that causes rearrangements on the chain. And lambda is kind of the typical distance at which the first rearrangement happens. Okay. So you're not surprised to learn that if you look at sizes significantly less than lambda, you don't even see this first rearrangement. So you declare that that's just localized, right? And you need to go to system sizes significantly larger than this lambda scale, which is a finite scale, but we can estimate it, and it's comparable to the system sizes that people can do. That's why we've drawn the black dashed line up there. It's only when you go to L much, much larger than lambda, you're going to realize that there is a critical point that can be delocalized because you've allowed these resonances that do happen in the thermodynamic limit to, or larger sizes. You don't need to go to L to infinity. You actually can see them now, okay? And so I wanted to tell you about the finite size drift you see in exact diagonalization. So let me really zoom into this plot at these 1 over L's that, in this cartoon are accessible to EV. So what's going on there? Red region is thermal. Blue region looks localized to you. Remember, this is all finite size crossover. So all these dashed lines are finite size crossovers. So if you take cuts through this diagram, varying W over J, at different L's. Those are my purple lines. What you see, well, the boundary between the red region and the blue region just drifts to the right, right? And yeah, that's it. Just to the right, we can make more compelling plots for this, and I'm happy to show it to you. But this is the linear drift that we predict with L, and we would thus predict that when you go to significantly larger L's, as larger than this first resonance length that I introduced, it would stop. Okay. Tom, if I started a few minutes late, should I keep going? Or
yeah, that's fine. That's fine. Yeah, you can keep going for a few minutes. We started a bit late.
For a few more minutes? Okay. I will, I'll try to get to it. I'll stop in order 3-4 minutes, okay?
Yeah, that's perfect.
Okay, so let me summarize what we would say about the MBL-thermal transition, because a lot has been said about it, and many of the things that have been said about it are contrary to what we're saying, so I just thought it's useful to lay it out. So going back to that plot up there, it's localized at small l, delocalized at large L. What's small, what's large? It's comparing to this resonant length that we've introduced called lambda, which depending on the setting, we can calculate it for flow K, we can calculate it for an energy conservation case, but it's a polynomial of W over J. Like, so it's a polynomial of something that's large at the transition. That is to say that the critical values of W over J that people see numerically is, order 10. So that's what leads us to believe that this resonance length is not a lattice. Well, it's one order of magnitude, at least if it's a lattice scale. And we're predicting a continuous transition, which is to say no jump in local quantities. And here I want to just make a connection to some earlier work. I certainly know Vedika's on the Zoom call, maybe Tyrone is too. Where they, so Tyrone had, this was a long time ago now, had predicted that the entanglement entropy of subsystems of the transition should be a should obey the volume law, and should be as if it were in the thermal phase. And I don't know that we've not quite calculated that, but at least for us it looks delocalized. So it's consistent with that, let's say. And we would explain the results that Vedika et al. Noted about the transition looking localized at small sizes as being a small size effect. That if you went to L's much larger than this resonance length, you wouldn't see that. And finally, as I already said to Vedika, this is the asymptotic scaling it is possible that this is asymptotic scaling for sufficiently high uniform potentials. It cannot be the asymptotic scaling for truly disordered potentials. I'm happy to discuss how and where this might apply and how that physics can change. Well, we don't fully understand how the physics will change, but I just wanted to place in context that I believe, or we believe, that all the phenomenological RG studies that have been done to date are in the regime where kind of the Harris-Lux scaling length becomes important. So much closer to the transition. So going up, sorry, might be helpful to look at this figure. Look at that semicircle there. We're kind of saying you need to zoom in on the transition at these very small deviations and very large lengths for that physics to change this asymptotic scaling here with disorder. Okay. Now I will go for just, I'll give you a quick, maybe 1-minute version of what we're doing, because you probably are wondering how do they manage to get all these great curves with all these exponents. So like I said before, we have a probe spin that we're connecting to a chain. And what is our model of the chain? Our model of the chain is just the model of the matrix elements of this operator V that connects the probe spin locally to the chain. Okay, so for those among you who have done this stuff before, if there was a model of L bits around, what we're kind of saying is that the norm of the operator decays with range as J e to the minus R over zeta, where the way you think of the range is kind of like, what is the range of the L bits that are being rearranged around the point that we've connected this probe spin, okay? And yeah, we can generalize this without appealing to range, this kind of range dependent model, but can leave that be. And so you see, starting from that, you can actually repeat the kind of usual comparisons of matrix on level spacings that people do to derive a stability criterion for MBL. In the interest of time, I am not going to go through this one line of algebra, but I just want to say that we get the same criterion that you would from thinking about rare regions that you couple into these chains, except there are no rare regions here. This is just coupling in one probe spin, and you're not thinking about a typical part of the chain and typical scale of the matrix elements. And so there was also noted in a recent paper by Brian Clark, so that this criterion may have nothing to do with rare regions. And this regime was previously called strong MBL by Nankishore et al., but we would say that's the only MBL possible when you connect it to probes, only stable MBL possible. You know what? I'm going to simply tell you this picture, and then maybe open up for questions. So what are we basically doing? We couple this probe spin in, and we're in the business of identifying resonances. So resonances are basically, at each range we ask the question, is the matrix element sufficiently large that you are able to exceed the bare level spacing and thus couple two states in the two states that were a product state between the chain and the probe element. And every time we identify such a resonance, we form cat states. And then we add their contribution to the spectral function as two delta function peaks at the matrix elements at that range. Okay, I might have gone too quickly, but that's part of what we're doing. All we're doing is carefully statistically counting the resonances, and every time we see a resonance, we're adding kind of a delta function contribution to our spectral function. As you look over different states, this mu of R will vary around, either because of statistical fluctuations of mu of R at the same range, or because the range itself that you find the resonance is different. And then we add it all up. We add it all up, and we get a smooth curve. So that's what we've shown before. With energy conservation, resonance finding by range is trickier because it gives you an extra constraint. If you don't have a partner at the right energy, you cannot do any resonating. That's why we get these different results. And with that, I just want to thank all the agencies that support me. Thanks, Phil, again, for the great collaboration. Thank you for your attention. Sorry for running over, and happy to take questions.
All right. Yeah. So thanks, Anusha. It's very nice. So again, feel free to ask questions in the chat box or by raising your hand. It actually looks like we already have a question from Tarun. So Tarun, if you could unmute yourself and ask.
Hi, Anushya. I had a question. Thanks for the nice talk. You have this older work with Chris on titled semi-classical limit of many-body localization transition, where seemingly you had an example where you can do basically solve pretty much everything, and you had this percolation transition and so on. And I think the localized regime was non-ergodic and so on. But does it not give any insight into these questions about drifting? And given that that was such a really simple model, and yeah, if any, but what does it teach us about this?
Oh, yeah, okay. Thanks, Karen. Maybe you're the only person who read that paper. I don't know. It feels to me like it was lost in time. So what do we do there in light of all the random circuit stuff everyone's talking here? We were thinking about Clifford circuits and how random Clifford circuits might capture the dynamical transition between localized and thermal phases. But in answer to your question, the problem with it was that we were in this class of simulable circuits, which is Clifford circuits, where we were able to sharply map the problem to a percolation problem on a graph. So the exponents that we derived were percolation exponents. In particular, in 1D, there it is all localized.
Of course.
Yeah,
yeah, I was thinking of 2D. Yeah, right. Yeah.
Yeah. So in 2D, the hope was that it might have given us some starting point to do something more interesting in 2D. We never figured out how to controllably deform from that point. Maybe there's some knowledge since in this community studying random circuits more seriously. But yeah, that was the status of that. It was a special solvable point in 2D. It had these features. I don't think anybody believed well, now I think people might say rare regions destroy the localized space in 2D. Even if there was a notion of a sharp transition, I don't think anybody believes the thermal phase would be delocalized, non-ergodic. It was all very special features of a solvable model.
Okay.
Yeah.
Okay. Yeah, that's all. Thank you.
Okay, we have a question from David.
Yeah, hi. Yeah, right on this figure right here, right, you've got the critical fan, and we're very familiar with the crossover on the left in this problem, but
Okay.
you're showing a crossover on the right.
Yes.
I wonder if your model has any hints of how to see that. You've shown it here extending up into the regime that's numerically accessible.
No,
So
no. Okay.
Dotted
Sorry.
line up in the upper right-hand corner. How can I find that line?
No, so David, great question. We should not have drawn, I mean, I don't, I think Phil's changed the type of dash, but from the bottom to the top, but we should not have drawn the line there. It was just to mark that it was 1/c. To see the fact that there is some, the other side of the cone, so critical to MBL, you have to go to L much greater than lambda, and then, then I would, you would see these knees. The knee that I have in my blue curve, for example. That requires you to be at L's much greater than lambda to see the finite size crossover from critical to localized.
So in the blue curve on the right, or now it's on the left, you have a feature, and you're saying that would never be numerically accessible?
No, so is there here? Hold on. Actually, there is a way for me to point like this. Okay, so all we're the blue region is fully localized, right? Or it's localized as determined by its order parameter. So we're saying what you see in ED is this transition here, and that's what you and Vedika, Johnson and noted before.
But you're showing a crossover on the right side between
which I should not have drawn this here. I'm saying that I should only draw it here.
And why, why would it ever slope that way, and why would it stop being present once you got up to the scales?
Well, I mean, we're doing a finite size asymptotic scaling theory should only work in the limit 1/L to 0, right? All we're saying is that there is a finite size scale we can estimate, below which you don't even see the resonances that would give rise to the delocalization and the asymptotically large L transition. So, yeah, is this the scaling regime for that transition? No, no, you don't see anything here, and you need to go down in here at large enough L to be able to actually see both.
But what would we look for down there?
You would look for which one's a good curve? Yeah, let me show you this one. You'd look for the knee, yeah.
And you're saying that knee will never be present in the numerically accessible sizes?
No, because the whole critical cone looks localized. You basically don't see this regime, whatever it is, in flow K or yeah, you're just not sufficiently close to your L's are not large enough for this scaling theory to even apply with this thing setting the crossover.
Okay, so we have a question from Tibor.
Yeah, thanks. So I was wondering that now with this understanding at hand, does it give you like the ability to try to come up with some model where you can tune this new scale lambda, make it small enough that you can actually see these effects in ED?
That's a good question, and I think I will speculate here. We're not sure. So, but which is just to say, I think flow K is a good place to look for two reasons. Let me just go back to this flow K thing. Maybe here, no. Here, just so that you can just see one plot. So in flow K, what's interesting is that at the transition, we're actually predicting something that is not 1/omega, but 1/omega corrected by theta c. And this theta c, where is it? Okay, so if you have it up here, and this is the same, this omega over j is this lambda parameter. So basically, if you're able to make this theta C large. So that is to say, you kind of want to have that the finite size transition that you see are when, so this is okay, when the drive frequency is comparable to J, which is not where anybody sees their finite size transition, right? Usually you see it at omega over J, much, much greater than 1. But if you can tune yourself to kind of get that ratio to be smaller, I think you're in the business of making this resonance length shorter and can test some of these things. I mean, maybe we're wrong, but it would really be interesting to try to test it. And then we have sharp predictions for what you should see. So if you can make this length shorter. So that's where I would try. If I were going to try to do this, I would try to go to massage or Floquet model. Because there are two things you can vary there. W over J and driving frequency over J. So if you can kind of play with them, you might be able to.
I see, thanks.
Okay, and it looks like we have a question from Drew in the chat box.
Yeah, I was just wondering a little bit about, on this diagram, you have that the critical regime itself is delocalized. I was wondering if you actually mean that it's delocalized, or, I mean, I guess in the RG treatments, for whatever this is worth, we find that most of the configurations at the critical regime would actually be localized.
So let me comment on, okay, so, right, as Vedika maybe asked already, this is not, with disorder, this doesn't even obey the Harris-Luck criterion, right? Where I have it. I wrote it out explicitly so that you would see it. Right, we're predicting a diverging, this is really a diverging range scale, range of rearrangements of velvet. But I'll call it length. It's a diverging scale with an exponent that doesn't obey the Harris-Luck criterion for disordered systems, right? So let me tell you where I think this fits. In the RG, you start with models that apparently locally, you just say they're thermal or they're localized. And then you make up a bunch of rules for how to like glom them up and how they look, right? Now, we think the scale to which you should coarse grain in order to even start talking about thermal or localized is this C. And then, which is only kind of, so we think there's a pre-asymptotic regime where this theory holds. And as you go to very, very large L with in disordered systems, maybe, I don't know whether all the RGs agree. I think KT seems to be something creeping up everywhere. So maybe some physics like that emerges when you coarse grain to the scale psi to C to start applying the RG.
Yeah, I guess I would push back a little bit on the need to coarse grain to C, which could be arbitrarily large. I mean, I think to define thermal or localized, you just need subsystems to be much larger than the lattice spacing. I mean, if C were infinity, you could still talk about whether.
I would disagree because I would disagree because like so I'll tell you where it comes from for us, and I know this is an ingredient in all the RGs. So you know, in many RGs you kind of have this, where'd it go? Here. You kind of put in, this is this zeta, right? This thing that controls how quickly matrix elements are falling. And in particular, this is what Dirac and moving mirrors would have placed a bound on. Now, my understanding is this is a parameter in the RG and it flows and so on. But what we're saying is that to be able to tell the difference between zeta and zeta C, you need to, when zeta starts becoming very close to zeta C, you need to go to a pretty large diverging length. So it seems I would push back on saying you know what's thermal and what's not, if what your underlying matrix element model, which kind of builds in which side you're on, is something like this. I'm happy to discuss it, but this is my understanding.
Yeah, maybe this is better for the breakout rooms, perhaps.
What's that?
Might be best saved for the breakout room.
Yeah.
Thanks.
Okay, yeah, and then since we did start a little bit late, so I'll Vedika has a question, and then we can move into the breakout rooms for the rest of the conference.
I actually had the same question as Drew. So.
Oh, okay, perfect. So maybe let's go to the breakout rooms then.